Bismillahirrahmanirrahim. Assalamu alaikum. In today's lecture, we will be discussing molecular orbital theory, or MOT. MOT is actually based upon the wave nature of electron. So, according to the Schrodinger's wave equation, we have different solutions for Schrodinger wave equation, and it gives rise to the electron density that we call as the atomic orbitals. So when electron is considered as a standing wave and it circles around the nucleus, it generates electron density. The electron density for example, s orbital that is spherical in shape, in cross section this could be shown in this way. And here we can see that this, if suppose this is nucleus and we are moving away from nucleus toward outside, there is no electron density for time being, and then at a certain distance there appears a little bit electron density. It deepens, it becomes maximum, and then this further fades out, and then it reaches up to zero. So this is the region where this electron density is maximum, or it appears for within an atom. This region is called as the atomic orbital. So molecular orbital theory, actually this is based upon the idea that the atomic orbitals, they combine together so as to give rise to the molecular orbitals, while the atoms are combining together in order to give rise to the molecules. So before we discuss molecular orbital theory in detail, we have to discuss some properties of the waves when we take electron as a wave. So each wave consists of two parts. We know that if suppose this is the reference line, suppose this is the reference line, and this is one part of the wave, the second part of the wave. So we have a part of the wave above this reference line of the coordinate axis, and then the part that is below this line. So the upper part, that is called as the crest, and this lower part, this is called as the trough. So in the coordinate axis, this upper part is in the positive phase, and this lower part is in the negative phase. So this is according to the coordinate axis, that above this line this is positive, and below this line this is negative. So these two parts of the wave, these are shown as positive and negative. This could also be shown in different colors. For example, if we draw the same wave, we can show its different parts in different colors. Suppose we have the reference line, and we want to show two parts of the wave. One will be shown in red color and the other one in blue color. So these are two ways, and these could be shown in the shaded area, or completely this could be shown in colors. So this is just to distinguish between these two parts. So when the waves combine together, that will happen actually when the atoms combine together, and we are considering the wave nature of electron. Suppose we are taking this wave, so this is one of the waves, and we want to combine that wave with another one. So how do the waves combine together? There are two ways these waves combine together. One is they'll combine together while they're similar phases. These are reinforcing each other, positive with positive and negative with negative. And the other one will be that the positive will be coming in front of the negative one. So let's see what will the result when these two waves overlap with each other. So this is one of the waves. If suppose the second wave, it comes near to this wave and it completely overlap. This overlapping may be complete overlapping, this may be partial overlapping like this, and there may not be any overlapping. So these are the two ways these waves could combine together. That is, they could overlap completely or to some extent, or they cannot overlap at all. So if, for example, they overlap each other, what will the result? The result will be that the amplitude of this wave will increase. Towards both positive and the negative phases. So this is called as the constructive combination of the waves. This is constructive combination. And when atomic waves combine together, actually this is the constructive combination that results into bond formation. The other way is that these waves come near to each other with opposite phases. Let's see what will be the result. We have one wave and we have the second one. So if they come close to each other in such a way that there is no overlap, here the positive phase is coming in front of the negative phase. So there is no reinforcement of the crest with crest and trough with trough. So what will the result? The result will be that these two parts of these waves, that is positive opposite to negative, they will just cancel each other, and the result will be that there will be no when they cancel each other, there will be no wave at all. So these waves, they will be just canceling out each other because of their opposite phases are facing that are facing each other. So this way of combination is called as the destructive combination of the waves. This is destructive combination. And here, no bond formation will happen. So bond will be formed only when the similar phases of the waves they come they combine together, and the amplitude of the resultant wave will be increased. So this is the basis that actually underlies the concept of molecular orbital formation. Now we look at some specific examples of the atomic orbitals when they are going towards the formation of the molecular orbitals. Now, molecular orbital theory postulates that the atomic orbitals combine together so as to give the molecular orbitals. The combination of atomic orbitals, according to molecular orbital theory, uh, occurs in a mode that is called as the linear combination of atomic orbitals. That is, the atomic orbitals will combine in a linear fashion. So, if for example here, to start with, we take the example of hydrogen atom. So hydrogen atom in its ground state has its electron in 1s orbital. That is there is only one s orbital in the first shell of hydrogen. So hydrogen, it has atomic number 1, so only one electron is there, and that one electron is present in the first s orbital. And we know that the shape of the s orbital, this is like a sphere, and here we will show this sphere with the help of a circle. With this nucleus, suppose this, we have two hydrogen atoms, and we want to combine their atomic orbitals so as to give rise to the corresponding molecular orbitals. We can label these orbitals as, for example, this is the first one. We say that this is HA, and this one is HB. They combine together. Now we are here, this orbital, we know this is electron density, and this electron density, this is based upon the wave nature of electron. So we'll consider this electron density and this electron in both of these atoms as the um, waves. So as we have seen that waves could combine in two ways, so similarly these atomic orbitals, they will be combining in two ways. That is, the phase of these two waves, they may combine together with in phase combination, and the other one is out phase combination. So two possibilities are there. We will take these two possibilities separately. So we have two possibilities. In the first one, suppose these two atoms combine together, that is their orbitals, they are mixing up together in a way that when these atoms combine together, their electron density takes this form. Suppose the electron density of first atom and the second atom. When these orbitals combine together, we see most of the electron density, this is away from the nuclei, and the nuclei are close together. This is one of the two possible situations, and it happens when these two waves, that is the wave functions of these electrons, they combine together with the out out phase combination. The other possibility is that they combine together by in phase combination. So when they combine by in phase combination, the result will be like this. Here we can see that these two nuclei, they are having much of the electron density in between. That is, this volume is showing the electron density, and here the electron density is away from the nuclei. So we can say that here the positively charged nuclei contain negatively charged electron density in between them. So what will happen? There will be strong electrostatic force of attraction upon this electron density. Remember, this electron density is for two electrons, one from atom A, the other one from atom B. So there will be overall attraction between these nuclei. As a result, the energy of this system, this will be lower as compared to these combining atomic orbitals. So we take this orbital a little bit lower if we take into account the energy of the system. Suppose this is the axis of energy. So we have energy here, and we see the energy of the atomic orbitals is higher as compared to this molecular orbital. This is the in-phase combination of these wave functions of these two separated atoms so as to give rise to this molecular orbital. This molecular orbital that contains electron density in between these two nuclei, this is called as the bonding molecular orbital. It will be lower in energy as compared to the individual atomic orbital, total energy of the individual atomic orbitals. And this is because of the in-phase combination of the electron densities or the wave function. And here, when we see that this positively charged nucleus and this positively charged nucleus, they don't contain too much of electron density in between them. Rather, electron density is away from these nuclei. So the result will be strong forces of repulsion. Now, this region that doesn't contain electron density, this is called the nodal region. So this is the nodal region, or simply this is called as a node. So the combination of two 1s atomic orbitals, it results into formation of two, it may result into formation of one of these two molecular orbitals. So now the force of repulsion between two nuclei, it will make this orbital go higher in energy as compared to the energy of the combining atomic orbitals. Now, if we show the same process with the help of a diagram, it will be like suppose we have one of the 1s orbital, it has one electron. So suppose this is one s orbital, the other 1s orbital also contains one electron, and here we are taking the energy axis. So one possibility is atomic orbitals combine together to give rise an orbital that contains the electron density in between two combining nuclei this way. The other one is the nuclei is away, the electron density is away from the nuclei of the atomic orbitals, combining orbitals. So these are two atomic orbitals, two possible molecular orbitals, this one with lower energy and this one with higher energy. The electrons will be occupying the lower energy orbital, and they will be just following the rules for the filling of the atomic orbitals. So these are the atomic orbital, and these are the molecular orbitals. Now we see here that the electron density in case of this orbital, molecular orbital, this is symmetrical around the axis joining these two nuclei. Here also this is symmetrical around the axis joining the two nuclei. So this kind of electron density is, its symmetry is said to be sigma symmetry. So this orbital will be called as a sigma orbital. And the corresponding high energy orbital is called as the sigma star orbital. And these combining atomic orbitals were 1s, so this sigma will be sigma 1s. This sigma star 1s. So this is the situation in case of hydrogen. And when this electron density is between these two nuclei, this is called as a chemical bond. And here, when there is no electron density, we say that there is no chemical bond. Now, the points that we have to remember here while we are discussing the formation of these molecular orbitals from the atomic orbitals, this is that the atomic orbitals give rise to molecular orbitals. And this combination happens in a linear way, that is the linear combination of atomic orbitals. And these are bonding as well as anti-bonding molecular orbitals. And we have seen that the bonding molecular orbital, they are lower in energy as compared to the energy of the atomic orbitals. And the anti-bonding molecular orbital, they are higher in energy as compared to the corresponding atomic orbitals. And the electrons in the atomic orbitals, while going towards the molecular orbital, they will be filled up in the low energy molecular orbital. And these electrons actually they hold these two nuclei together, so these are said to be making a bond. Now we look at the combination of other type of atomic orbitals. For example, in organic chemistry, we talk about the um, second shell, that is in case of carbon, nitrogen, oxygen. These are the common atoms that actually are constituent of the organic compounds. So we'll be talking about the combination of the orbitals that are present in the second shell. The combination of the p orbitals. We know that p orbitals, in all the atoms, they start from the second shell. And here we will be concentrating upon mainly carbon, as essential part of organic chemistry. So in the three dimensions, we first draw the p orbitals, and then we look at the combination of these p orbitals. How does it happen? Suppose these are our coordinate axes. We have p orbitals there are three p orbitals, one about, suppose, x-axis, the other one about y-axis, and the third one about z-axis. So we can assign these as px, py, pz. We may also call this one as pz and this one py, or this one pz, this one as px, doesn't matter. So this is p. Now we can see that in case of p orbital, these are dumbbell shaped, and these two lobes, they actually show two different phases of the same wave. That is the positive phase and the negative phase. As we know that each wave, it has two parts, that is one crest, one trough. So the crest, this is above the uh, coordinate axis line, so this is shown a positive sign, and the trough is below the line, so this is given a negative sign. So this must be shown separately, that is the two parts of each p orbital, they must be shown differently. So there are different ways we can show these two parts differently. One is that we just show with the help of plane area and shader area, and the other one is we show these orbitals with different colors. Suppose one phase as blue color and the other phase as red color, and these could be completely filled up with color or just shown with the outline. So these are different ways. And another one simple way is just having p orbital as outline in any color and assigning positive and negative symbol. So we won't be using these positive and negative symbols because these may interfere while we are discussing, for example, child species, so they may misguide the students. So I will not be using this one. Throughout the lectures, we'll be using any of these two, and it is the notations while discussing the p orbital. Now, if we want to combine two p orbitals, Suppose we are having these p orbitals, and here I'm going to show these with the help of shaded area and plane area. So these are the p orbitals. Suppose we want to combine these. This p is the p orbital from second shell. Suppose these are three 2p orbitals. 2p. We want to combine this 2p from one atom with the 2p from another atom. Suppose suppose they are combining together. We want to look at the mode of combination. How do they could combine together? Suppose they are coming close together. Two px orbitals, two py orbitals, two pz orbitals. They are combining together. We are showing all of these together just to make our understanding simultaneously about these orbitals, the way they are combining together. Then we will be considering these separately also in order to better understand. So here we can say see that these three p orbitals, they are combining with three p orbitals from another atom. Total 6 atomic orbitals are combining together. So total 6 molecular orbitals are possible. One way is what we have shown here. The other way, this will be, okay, first we discuss this one. If you look at px orbital, so for sake of our convenience, we are making a little bit change in this p orbital. And the shaded area we make towards right side, so that when we combine these together there may be some ease of understanding. So we have talked about two types of combination. One is in-phase combination and out-phase combination. Now let's look at what happens when these atomic orbitals combine together. Now these p orbitals, when they are going to combine, they give rise to two types of situations with respect to the ways they'll be going to combine together. Now look at this p orbital. While they are coming together, we have these two p orbitals that are combining in this approach. That is, we can say this is end-on or head-on approach. End-on or head-on approach. What about these p orbitals and these p orbitals? They are combining in a way that is somewhat different, and this is like they are approaching each other this way. So only these parts they are going to approach each other, and there will be partial overlap. There is much overlapping. Here is partial overlapping. Similar is the case with pz orbitals. So this one is called as the sideways or side-on approach. So when head-on or end-on approach happens, the electron density, this becomes symmetrical about the line combining the nuclei of these two atoms together. So this will be symmetrical if we rotate about this axis. This electron density will be symmetrical. So this bond will be having a sigma symmetry. This is called as a sigma bond. Whereas in both of these cases, when these py are combining, pz are combining, so they'll be giving rise to an electron density that will not be symmetrical when we rotate about this axis. So electron density will be above this line or below this line. Similarly, away from this line or towards us. So this electron density will be different when we rotate about this line combining or this axis that is joining the nuclei of two atoms. So this symmetry is called as pi symmetry. This is pi symmetry, and the bond formed will be a pi bond. Here sigma bond and here a pi bond. Now we consider the molecular orbitals that will result from this combination separately by taking px, py and pz orbitals separately. Suppose first we look at the combination of px orbitals. This is one of the px. It combines with another px. Suppose we show this way. This is 2px. This is 2px from another atom. So when they combine together, two possibilities arise, just like the formation of 1s1s combination, the bond formed as a result of combination 1s1s orbital. So here two possibilities will show different ways. Suppose we bring about a little bit change here, and we make this one as shaded area. So the first possibility, this will be that these two px orbitals, they are approaching each other with same phases. So when they approach each other with the same phase, the result will be lowering of energy, because the electron density will be in between the two nuclei of the combining atoms. Much of electron density will be between the nuclei of two combining atoms. So this is the electron density. We can show with green color. That is the maximum electron density, although this one is also electron density, but very small density, that is towards the other side with a different phase. Now when these two atomic orbitals, they combine with out of phase symmetry, the result will be the electron density between the nuclei of the combining atoms will be very small, and much of the electron density will be towards opposite directions, positive, and this one negative. So because similar charges are approaching each other, so there will be increase in energy of the system. So this orbital will be higher in energy as compared to the combining atomic orbitals when we are considering the energy also. Suppose this is the energy axis. Well, similarly for p orbitals, p y and p z orbitals, suppose we have one p y orbital, the second p y orbital. Suppose the two phases are shown this way. They are combining together. Similarly, the other way will be like this. With the same phase. orbitals with the same phase. Now when the atomic p y orbitals approach each other, they can do in two different ways. That is, their phases of the waves are same, or these are different while they are approaching each other. So when they are approaching each other with the same phase, the result will be that the electron density will be above the plane and below the plane. And this is the nucleus, and this is the nucleus, and we have this one, two different phases. So we have electron density above the plane and below the plane. And here what will happen, because these are out of phase, so there will be no combination, rather the electron densities will be moving away from each other, and the result will be that almost no electron density between the two combining nuclei. Now here again we have positively charged nuclei and negatively charged electron density in between the nuclei, and here two positively charged nuclei, they are approaching each other, electron density is away. So as a result, the energy of the system here will be lower as compared to the atomic orbitals, and the energy of system here, it will be higher as compared to the atomic orbital. Now these two molecular orbitals that were formed as a result of combination of these px orbitals, these are having this electron density symmetrical about the line of the line that is joining the nuclei. So we say that it has sigma symmetry. Here also it has sigma symmetry. So both of these are, bonds are the sigma bonds. And this is sigma px, and this p is from second orbit, so sigma 2px, and this will be sigma star 2px. When we talk about these two p orbitals, here this symmetry, sorry, the phases are shown as, so here this one having the electron density away from this line, above this line and below this line. Similarly here, electron density above and below. And if we rotate about this line, this axis, the electron density is not symmetrical. So this is called having a pi symmetry, and this is a pi bond. This is also a pi bond. This will be pi 2py or 2pz, and this one is pi star 2py or 2pz. So this is the way these p orbitals, they can combine together so as to give rise these sigma and pi bonds. Now all these three p orbitals, when they combine together so as to give rise to the molecular orbitals, as we have seen previously, they don't result into formation of all of the molecular orbitals similar. Rather, there is uh, differences of the molecular orbitals that are produced as a result of the combination of these atomic orbitals. So here we are showing that how do these orbitals are approaching, as we discussed before. So these two sorts of molecular orbital arising from the combination of these p orbitals, they are not same. That is, we say that they are not degenerate. Rather, more overlap is possible when px orbitals, they combine together by end-on or head-on approach, as compared to when the py and pz orbital, they do so by their sideways approach. So this could be shown with the help of diagram when we are talking about the overlap as a result of lowering of energy. We see that as much overlap is there, as much lowering of energy will take place. And in case of these linear over, sorry, this head-on overlap, there will be much more electron density between the nuclei as compared to sideways approach. So the energy minimum will be much for the head-on approach as compared to the sideways approach. So when we talk about uh, these three p orbitals, and we want to draw as in the form of energy level diagram, it will be something like, suppose this is our energy axis. We have our three p orbitals. These are the p orbitals, 2p, 2p. So out of these 2p, two are the px that are combining by head-on or end-on approach, resulting into formation of sigma bond. So this is sigma 2px, and if they combine by in-phase combination, but by out-phase combination, this will be sigma star 2px. So the px orbital will be combining so as to give rise to sigma px orbitals. And these py and pz orbitals, when they combine, their overlapping is similar, so their energies will also be similar. That is, their molecular orbital will be degenerate, that is, having the same energy. So these are the pi 2py and pi 2pz. They will be having same energy, and if they are combining in out phase combination of the wave functions, then they will be pi star 2py, pi star 2pz. So we show this with different colors. This is just to have a diagram to show that these atomic orbitals are combining to give rise to these molecular orbitals. So if we want to fill up the electrons, the number of electrons in, for example, carbon, suppose P contains, suppose we have another example like we have nitrogen. So in nitrogen we have three electrons in the p orbitals, that is one electron in each of the p orbitals. So these will be filling up in increasing order and following the rules governing for the filling of the atomic orbitals. So for example, in case of nitrogen, these electrons, they will be going towards only molecular orbitals and the bonding molecular orbitals, whereas the anti-bonding molecular orbitals, they will be remaining empty. If we take the example of, for example, carbon, we have only two electrons in the p orbitals. So these will be having, for example, if two carbon atoms are combining together, so their um, p orbitals, they will be having only this type of situation. In case of oxygen, we can have one extra electron as compared to nitrogen, and we'll be having two unpaired electrons in anti-bonding molecular orbitals. So here we have looked at the combination of the p orbitals. Now if we want to know about the combination of one s and one p orbital, suppose we talk about one s orbital that wants to combine with a p orbital, nucleus here, nucleus here. So suppose these are two phases of the p, their combination will result into formation of this molecular orbital, or the other possibility is it will be going towards forming a molecular orbital with suppose different phases, and the result will be there will be a node in between the nuclei of the combining atoms. That is, there is no electron density here. So it will be having a bonding molecular orbital and anti-bonding molecular orbital. So this one is, because this is also end-on approach or head-on approach, so it will be giving rise to sigma 2s 2px, and this is sigma star 2s 2px. So this will be higher in energy and this one lower in energy. The electron, they will be going first towards this bonding molecular orbital and then towards this anti-bonding molecular orbital. Now we want to talk about, this is the bonding. Now we want to talk about the, what about the opposite of bonding, that is bond breaking. So if we want to break a bond, these electron has to be moved from the bonding molecular orbital to the other possibility, that is the anti-bonding molecular orbital. So electrons will have to be removed from these in order to go towards the higher level of uh, energies. So it will require energy. So bond breaking process, it will need energy in order to promote these electrons towards the high energy levels. So this way we can break up the bond, as we will discuss while we are going towards some specific reactions. So in this lecture we have talked about the formation of chemical bonds as explained by molecular orbital theory. In the next lecture we will be talking about the hybridization process, as it explains the formation of some specific structures of the molecules. So uh, that is another concept that we must have an understanding in order to explain the organic molecule as well as the organic chemical reactions in a better way. Okay, see you in the next lecture. Assalamu alaikum.